Okay, so today we will continue on in Chapter 9, where we are conducting inference for numeric variables. Okay. And so on Monday we covered the central limit theorem, sampling distributions of the sample mean x bar, and today we'll get into applications of all of this. So okay, and so as far as inference goes, we have 4 topics: confidence intervals for mu based on one sample, we also have hypothesis tests for mu based on one sample. We have confidence intervals for mu1 minus mu2 based on 2 samples, and then we also have hypothesis tests for mu1 and mu2 based on two samples. Okay, and so on Monday we kind of just touched on confidence intervals for mu based on one sample. Today we'll flesh it out a little bit more, and we'll cover hypothesis tests for mu based on one sample, and then on Friday I'll cover both of these. There is a lot, but a lot of it is parallel to confidence intervals and hypothesis tests for proportions, which we have already covered. And so a lot of things should look quite familiar, at least with the line of thinking and all of that. So let's take a look. Okay, so we have confidence intervals for mu based on a sample. Okay, and so in your notes, what do we put in the middle of this confidence interval? We would put in the middle goes our best guess, right? For mu. I covered this, right? Okay. Just I teach multiple classes, and sometimes I'll get mixed up here. Okay, so we have x bar plus or minus our margin of error, which consists of a critical value times the standard error. Okay, and so what we will use for our critical value comes from our t distribution, and our standard error. Because we don't know what sigma is, we use s as a stand-in for sigma, and it's going to be s over the square root of n for our standard error. Okay, and again, the t distribution is very similar to our normal distribution, except it compensates for the fact that we don't know our population standard deviation sigma. Okay, so to select your critical value t star, you will look at the t-distribution table, okay? And you will need to know your confidence level and the degrees of freedom, okay? So you need confidence level and degrees of freedom. Which is DF, okay? So when we have one sample, or, well, we'll just say, our degrees of freedom is equal to n minus 1, okay? And this kind of comes from the fact that if we know the sample mean, one of these, so let's say you have 10 numbers, okay? And we're going to say that the average of these 10 numbers is 10, okay? So basically, once somebody reports to you 9 numbers, if you know that the average of those 10 numbers is 10, then that 10th number is determined, okay? And so, so you have only 9 degrees of freedom. So degrees of freedom is your sample size minus 1, okay? And then so what this looks like is that when you, let's say you had a sample size of 15, then, and you had a 95% confidence interval, okay? Well, if you have a sample size of 15, you would have 14 degrees of freedom, n minus 1, and at the 95% confidence level, at the top of the table, you'd go to the column that says 95%. You would use 2.145, okay? So because of the way the t-table is set up, we can only create confidence intervals with 80%, 90%, 95, 98, or 99. So we would not be able to create a 92% confidence interval, okay? But that's fine. I don't think very many people would ever ask for a 92% confidence interval. So anyway, you just look that up. Okay, so let's just try out a simple problem here. And we will say you take a random sample of 15, we'll do Jersey dairy cows, okay. All right, and so with 15, you know, and you would you measure their weights, right? Okay, and then so you get something like, you know, maybe one was 1,653 pounds and another one was 1,482 and 1,525, et cetera, et cetera, et cetera. Okay, so you have 15 measurements. Okay, so we will create summary statistics. And we would say the sample average, the sample mean, let's say, is 1,560 pounds. And the sample standard deviation is 158 pounds. Okay. So to make, so I'll say make a 95% confidence interval, and I will ask what is the lower bound of the interval. Okay, so go ahead and try that out. I'm going to create some answer choices here. go ahead and try this out. Okay, I'm going to hit stop in just a few seconds here, so get your clicks in, please. Okay. Okay, so I'm going to hit stop. All right, and so to solve this problem, let's identify what we have. Okay, so we have 15. This is our sample size n. N is going to be 15. The sample mean is 1560. So this is my x bar. And the sample standard deviation of 158, this is my s. So all we're going to do is just plug this in to x bar plus or minus t star times s over the square root of n. We look up t with a 95% confidence and degrees of freedom equal to 15 minus 1, or 14. And so we get 2.145 as our degrees of freedom. So I have 1560 minus 2.145 times 158 divided by the square root of 15. I end up getting 1560 minus 87.51. And that leads me to 1472.49. So it looks like most of you guys got that. Okay, so this would be my lower bound. The upper bound would be 1560 plus 87.51. So that gives me 1647.51. Okay, so this is my lower and upper bounds. And then we would say something like, I am 95% confident that the average weight of all Jersey dairy cows is between 1,472.49 pounds and 1,647.51 pounds. Okay, so this would be all Jersey dairy cows. This is basically in the population, the average weight of the population. That the population mean is between 1472.49 and 1647.51. Is that okay? All right, so just to make sure, this is kind of the same type of stuff we had before. So we have 1472.49 to 1647.51. Okay, so this is our 95% confidence interval for mu. So if I asked, does our confidence interval provide evidence that mu is equal to 1500, you would say yes or no. Okay, just a few more seconds here. I'm going to click stop. Okay, I'll click stop there. Let me ask another question here. Does our confidence interval provide evidence that mu is not equal to 1,500 pounds? Okay, again, get your clicks in. I'm going to hit stop pretty soon. Okay, click, click, click. Okay, I'm going to hit stop here. All right, so the answer to both of these questions is no. Okay, so 1,500 is in our interval. So 1,500 is between 1472.49 and 1647.51. Okay, but as far as it comes to answering these questions, so does our confidence interval provide evidence that mu is equal to 1,500? The answer there is no. Okay, all we can say is that 1,500 is a plausible value. Is a plausible value for mu. Okay, but but the interval does not say that mu is equal to 1,500. Okay, and again, 1,500 is a plausible value for mu. Okay, so we don't have evidence that it's not 1,500. Okay, so if you feel comfortable with confidence intervals for p hat, you should feel comfortable for confidence intervals with mu. It's just, instead of talking about the population proportion p, we're talking about the population mean mu. Okay, similar line of thinking there. Okay, I will move on then, and we will talk about hypothesis testing. Hypothesis testing for mu based on one sample. Okay. So hypothesis testing, we can break it down into those 4 steps again. The step one is to create our hypotheses. Okay. The hypotheses in this case is that mu, the null hypothesis always has an equal sign, and it's going to be mu is equal to some number, mu 0, okay? But keep in mind, mu 0 is a constant. So, for example, our null hypothesis could be something like mu is equal to 30, where, mu 0 is equal, mu naught is equal to 30, so our null hypothesis would be mu is equal to some number 30, okay? The alternative, again, is identical to the null hypothesis, except we replace the not equal sign, the equal sign with something else, like a not equal sign, or mu is greater, or mu is less than some number, okay? So it could be, the alternative would be mu is greater than some value 30, okay? So it's always going to be mu is equal to some number, and mu is greater than or less than or not equal to the same number, okay? And what you select depends on how the question is written, okay? What is step 2 when we did hypothesis testing for proportions? We would check our conditions. And I believe I've already covered checking conditions for the central limit theorem for numeric variables, correct? Okay. And then also select your alpha. Select or identify the significance level alpha. Okay, so that's the same. Step 3, as far as calculations go, we just have a few different formulas, okay? So step 3A will be find your standard error. So our standard error here is S over the square root of n. Then we get our test statistic, where we compare the reality versus the expectation. And so in this case, our test statistic will take on the letter T. And again, we do observed minus expected divided by the standard error. And in this case, our observed value is x bar. What we are expecting, though, if the null hypothesis were true, is that our samples to be around mu 0. So this is what we observe, this is what we're expecting, and we want to know, is there a significant difference between the reality and the expectation? So that's our test statistic. Okay. Once you have your test statistic, what is the next thing you do? So when you did proportions, what did you do? You got a test statistic z, and what did you do? You'd look it up on the z table, right? Same thing here, okay? So you'd look up the test statistic in the table, statistic t, and this time the t table. Okay, and this works quite different from the way the z table works. So it'll get its own slide. Okay. And then lastly, make your conclusion. So look up the test statistics in the t table. Okay. Oh, I'm sorry. To get a p-value. And then step 4 is make a conclusion. Right, and how do our conclusions work? If the p-value is greater than alpha, what do we do? we do not reject the null hypothesis. Again, don't write we accept the null hypothesis. And if the p-value is less than alpha, we reject the null hypothesis, okay? So the overall kind of outline of the steps that we do, I'm hoping looks quite familiar or quite similar to what we've seen already, okay? So let's talk about this thing using the t-table to get our p-value, okay? So this part works pretty differently from using the z-table, so let's talk about that, okay? So this will be step 3c, okay? So it's step 3c, so here we'll say, I'm going to just copy a section of our t-table. Okay, so this is what your t-table looks like. All right, so let's say you have done the other parts. Okay, let's say you have done everything else. Okay, and you have t equal to 2.45. Okay, and then your degrees of freedom, which is n minus 1, degrees of freedom is equal to 9, and the alternative has a greater than sign, okay? So this is what you need to know. You need to know your test statistic t, you need to know your degrees of freedom, and you need to know what your alternative hypothesis says. So if your alternative hypothesis has, let's say, you know, the alternative says mu is greater than 30 or something like that. Okay, all we would do is we look at 9 degrees of freedom. We just look at this row, 9 degrees of freedom, and we're going to say, okay, let's take a look. 2.45 fits between 2.262 and 2.821. Okay, 2.45 is in between these two numbers. Okay, is that okay with everybody? And then so you look at the top of your column, and we've got t right-tailed probability, and it says t.025 and t.010. Okay, so this means that if my test statistic ends up here, the corresponding tail area is between 0.025 and 0.010, okay, or 0.01. Is that okay? So basically, you're just going to look for your test statistic, and if it's in between two numbers, then you know your corresponding tail area is going to be in between these two numbers as well. Okay. So almost always, you will not get an exact tail area. Okay, you will almost never know what your tail area is exactly. Usually, you'll say, my tail area is between these two numbers. The only time you can say your tail area is exactly some number is if your test statistic ends up being exactly one of these numbers. So if you have 9 degrees of freedom and your test statistic ends up being exactly 1.833, then your tail area will be exactly 0.050, okay? Otherwise, you just say, oh, well, it's between these two numbers, so therefore my corresponding tail area is going to be between these two numbers as well. Does that make sense to everybody? Okay? All right, and so here are kind of the rules here, is that if the alternative has a greater than sign, then your test statistic t should be positive. Okay? You would look up the tail area, which is kind of the column headings, and then your p-value is equal to the tail area. Okay? If the alternative has a less than sign, then t should be negative. Okay? But the table only has positive values, so you just ignore the sign, ignore the minus sign, and look it up in the table. And again, here your p-value will be equal to your tail area. And so your tail area will almost always be in some kind of range. Okay? And lastly, if the alternative has a not equal sign, then the sign of t doesn't matter. Just look it up. Look up t in the table. Ignore the sign, whether it's positive or negative. Okay? And here the p-value is equal to 2 times the tail area. Okay, and then I'll put this here, and this is on a rare occasion, okay, so I'll say on rare occasion, so here I said if HA is greater than and T should be positive, or if HA has a less than, then T should be negative. In rare occasions, you'll have a mismatch, okay, where the alternative has a greater than, but T is negative, or the alternative has a less than and T is positive, okay? Then what you do is your p-value is 1 minus the tail area. But I would say that doesn't happen very often, okay? So if there's a mismatch, between the alternative and sign of t, then the p-value is equal to 1 minus the tail area. Okay? But I would say if that happens only if your data, if there's like a mismatch between your data and your hypotheses. Okay? So it's like, do we have evidence that the average, I don't know, the average weight of cows is over 2,000 pounds, okay? And then all of your data shows that the average weight is less than that. Of course, you're not going to have any evidence to support that the average weight is over that. So then there would be a sign mismatch, and then your p-value will end up being very, very large, okay? Because up here, the tail areas go between like, 0.1% and 10%. And then so if there's a great mismatch, then it would go from like 90% to 99.9% or something like that. So, but I would say this is a rare thing, so don't worry about it too much, okay? I would say these 3 rules up here will take care of most of your situations. Okay, let's just try another scenario here, okay? So let's say you have degrees of freedom equal to 10, and your t ends up being negative 4.75, and your alternative has a less than sign, okay? So what is the p-value? Okay, so now I will give you some answer choices. Okay, so pay careful attention to the column headings and your values here. You've got 10 degrees of freedom, you've done your math, the alternative hypothesis has a less than sign, and your test statistic ends up negative 4.75. So we'll say 10 more seconds to get your clicks in, 10 more seconds. Okay, get your clicks in, click, click, click. Okay, so let's take a look. So we're at degrees of freedom equal to 10. Okay, so we're in this row here. And we look at the last number and we have 4.144. So because we have a less than sign in the alternative, we're just going to ignore the negative sign. And we're going to look up 4.75 and we say 4.75 is bigger than 4.144. Okay? So that means our corresponding tail area will come from over here. Okay? So we're looking at this number. And so the question is, do I put my tail is greater than or less than this number? And what we see is that as far as tail numbers go, we have large tails on this side and we have small tails on this side. So because we're to this side, our tail area is going to be smaller than 0.001. So what we have is our tail area is less than 0.001. Because our alternative has a not equal sign, we're going to say our p-value, our corresponding p-value, will also be less than 0.001. So our answer choice is C. Okay? And likewise, if you end up getting just kind of a, if t were equal to negative 0.9, we would say 0.9 is over here, and therefore your tail area would be greater than 10%, and your p-value would be corresponding to be greater than 10% as well. Okay, we'll end there. We'll see you guys on Friday.